For centuries, we viewed the universe as a physical container, a dark room filled with tangible objects like stars, planets, and galaxies. We've mapped how these celestial bodies behave. Classical physics provides the mathematics to calculate how they pull on one another across that space. But despite the brilliant mathematical models built by the pioneers of modern physics, one question remains unanswered. Why does matter have an innate desire to attract other matter? If there's no underlying motive, why don't objects remain scattered as cosmic dust? Classical physics expertly describes the mechanical behavior of gravity, but it fails to explain the underlying motive or purpose for the pull. To find that purpose, we have to stop viewing the universe as a container and start viewing it as a massive information processor. Tracking the individual position and momentum of billions of scattered dust particles requires extreme computational power. In physics, this complexity is tied to information entropy. Keeping trillions of individual cosmic dust grains separate creates a massive processing load on the system. From an informational perspective, a disorganized universe is inefficient and constantly teetering on the edge of a system crash. Physicist Dr. Melvin Vobson proposes that this universal processor follows a specific set of rules, the second law of infodynamics. This chart shows how information entropy behaves in these systems. While physical entropy moves towards disorder, the second law of infodynamics requires that information entropy must decrease over time. To obey this law, the universe actively seeks ways to lower its computational load and optimize its processing memory. The universe has an innate, law-bound directive to compress its own data. Visualize a conceptual 10 by 10 grid of space. Placing 4 independent particles into this grid consumes 24.2 bits to track. But if the system moves them into a single cell, the information load drops to 8.1 bits. Because the second law requires this drop in entropy, the system exerts a physical pull to move these objects together. This corrective pressure to merge data points is the entropic force we experience as gravity. This explains why a sprawling cloud of cosmic dust eventually collapses into a dense planet. Clustering matter is the most efficient way for the universe to lower its entropy. Gravity functions as an entropic algorithm designed purely to compress cosmic data. If matter is just compressed data, what gives it a solid structure? Researcher J. E. Jimenez de la Garza suggests the universe's fundamental substrate is a vibrational field. Within this field, we look for phase coherence, the moment when scattered informational frequencies align and harmonize. When that phase coherence becomes fully stable, it creates a localized knot of information called a reality knot. These localized knots of highly coherent, low-entropy information are what we perceive as solid physical matter. Information entropy is the computational cost driving the universe to compress its data. Phase coherence is the structural language used to lock that compressed data into a stable form. The resulting compressed file from this process is matter, and the force executing this compression sequence is gravity. When an apple falls to the ground, the system is merging data points to optimize its processing power. The same rules apply to the clustering of a galaxy, pulling billions of stars together to minimize the system load. The universe functions as a massive, self-optimizing engine, balancing coherence and entropy to keep the fabric of existence from crashing.